ಗುಡ್ ಈವ್ನಿಂಗ್ ಸರ್. ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರಗಳು. ಇಂದಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಶ್ರೀ ಅತುಲ್ ಭಟ್ರು ಅವರು ಗ್ರಾವಿಟೇಷನ್ ಎಂಬ ವಿಷಯದ ಮೇಲೆ ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದು. ಸೊ ಅತುಲ್ ಭಟ್ರು ಅವರನ್ನು ಐ ವೆಲ್ಕಮ್ ಟು ಯು ಸರ್. ಸೊ ಅದೇ ರೀತಿ ನಮ್ಮ ಅಕಾಡೆಮಿಯ ಮುಖ್ಯ ಕಾರ್ಯನಿರ್ವಹಣಾಧಿಕಾರಿಗಳಾದಂತಹ ಡಾಕ್ಟರ್ ರಮೇಶ್ ಅವರನ್ನು ಕೂಡ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಸ್ವಾಗತಿಸುತ್ತಾ, ಹಾಗೂ ನಮ್ಮ ಅಕಾಡೆಮಿಯ ನಿರ್ದೇಶಕರಾದಂತಹ ಡಾಕ್ಟರ್ ಎ ವಿ ಬಸವರಾಜ ಸರ್ ಅವರನ್ನು ಕೂಡ ಈ ಒಂದು ವೇದಿಕೆಗೆ ಸ್ವಾಗತಿಸುತ್ತಾ, ಇಂದು ಹಾಜರಾಗಿರುವ ನನ್ನ ಎಲ್ಲಾ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರಿಗೂ ಕೂಡ ಸ್ವಾಗತವನ್ನು ಕೋರುತ್ತಾ, ಮಿಸ್ಟರ್ ಅತುಲ್ ಭಟ್ರ ಅವರ ಬಗ್ಗೆ ಒಂದೆರಡು ಮಾತುಗಳನ್ನ ತಿಳಿಸ್ಕೊಡ್ತೀನಿ ತಮಗೆ. Sir completed MSc in Physics from a Jain University, has been teaching physics since 2016 and working at PPC since 2019, and working as a coordinator of Purnaprajna Amateur Astronomers Club, working on popularizing astronomy among public through PAAC. Has been invited as a resource person for several Skywatch programs, talks on astronomy and physics, and has been published in peer-reviewed journal and has presented at national and international conferences. ಸೊ ಅತುಲ್ ಭಟ್ ಸರ್ ಅವರು ನಮಗೆ ಈಗಾಗಲೇ ಚಿರಪರಿಚಿತರಾಗಿದ್ದು, ಹಲವಾರು ಉಪನ್ಯಾಸಗಳನ್ನ PU ಮಕ್ಕಳಿಗೆ ನೀಡಿರ್ತಾರೆ. ಸೊ ಅದೇ ರೀತಿ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಅವ್ರನ್ನ ಈ ವೇದಿಕೆಗೆ ಸ್ವಾಗತಿಸುತ್ತಾ, ಸೊ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮವನ್ನು ಯಶಸ್ವಿಗೊಳಿಸಿಕೊಳ್ಬೇಕೆಂದು ಕೇಳ್ಕೊತಾ ಇದ್ದೀನಿ. ಓವರ್ ಟು ಯು ಸರ್.
ಓಕೆ ಸರ್, ಥ್ಯಾಂಕ್ ಯು.
ಮತ್ತೆ ಮಕ್ಕಳಿಗೆ ಸರ್ ಸ್ವಲ್ಪ ಈ ನಮ್ಮ JEE ನೀಟ್ ಮತ್ತೆ CET ಎಕ್ಸಾಮ್ಗಳ ಬಗ್ಗೆ ಒಂದು ಕೊನೆಯ ಒಂದು 10 ನಿಮಿಷದಲ್ಲಿ ತಾವು ಸ್ವಲ್ಪ ತಿಳಿಸ್ಕೊಡಿ ಸರ್. ತಮ್ಮ ಟಾಪಿಕ್ ಮೇಲೆ ಯಾವ ರೀತಿ ಕ್ವಶನ್ಸ್ ಗಳು ಬರಬಹುದು ಅಂತ ಒಂದು ಇದ್ರ ಮೇಲೆ. ಓಕೆ, ಓವರ್ ಟು ಯು ಸರ್.
ಸರಿ, ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಇಂಟ್ರೊಡಕ್ಷನ್ ಥ್ಯಾಂಕ್ ಯು. ಗುಡ್ ಆಫ್ಟರ್ನೂನ್ ಎವ್ರಿವನ್. ಇವತ್ತು the topic that I've chosen is gravity, because that's a very beautiful, at the same time very important topic when you talk about competitive exams also, because there are certain formulas that you need to understand before you attempt an exam, and you can just very small values and get different answers, several problems in through gravitational syllabus. Hagagi, we'll start with gravity. Most of us know what gravity is. It is something that we experience since childhood. One of the very first things we observe as a child once we stand up is how we fall, how things fall. ನಾವು ಮಕ್ಕಳಾಗಿರುವಾಗ ನಾವೇನಾದ್ರು ಎತ್ಕೊಂಡು ಹೀಗೆ ಬಿಟ್ಟಾಗ ಅದು ಕೆಳಗೆ ಬೀಳೋದನ್ನ ನಾವು ನೋಡಿದೀವಿ, ಅನುಭವಿಸಿದೀವಿ, ನಾವು ಬಿದ್ದಿದ್ದೀವಿ, ಏಟ್ ತಗೊಂಡಿವಿ. ಸೊ ದೀಸ್ ಆರ್ ದ ಥಿಂಗ್ಸ್ ದಟ್ ಯು ಹ್ಯಾವ್ ಎಕ್ಸ್ಪೀರಿಯನ್ಸ್. ಸೊ gravity is something that has been with you throughout your life. So it's easier to understand once you know the physics behind it. So when I talk about gravitation, we will usually start from the ancient philosophy, where Aristotle was the first one to talk about something falling. And Aristotle mentioned that things fell towards the center of the earth, which is the center of the universe, is what they believe. They thought that the earth was in the center of the universe. So everything fell towards the earth. Everything fell towards the center of the universe. Okay. So earth attracts all the mass in the universe towards it. This is what Aristotle said. And he also said that heavier objects fall faster than lighter objects. So if you have two stones and one is heavy and one is a small pebble, and if you drop, Aristotle says that the heavier stone should fall faster than the lighter stone. Okay, so this is an experiment that can be done on Earth. Something very similar is what you will observe. In ancient philosophy, also had Indian scientists like Aryabhata, who said that something holds the celestial bodies together. Otherwise, they would be all pushed away by centrifugal force. Because Aryabhata observed that the Earth is moving around the sun is there, and then all the other planets are moving around the sun. So if everything is moving in circular path, orbiting around each other, then there would be a centrifugal force. So if Earth is having centrifugal force, it is orbiting around the sun, then it should be pushed away by centrifugal force. Just like now the haggana tagondu, you take a thread and you tie a rock to it and you rotate it like this, and then when you leave the thread, the moment you let go, the thread will fall outwards, because there's an outward force called the centrifugal force. So if things are not going away because of centrifugal force, something is holding them together. That is what Aryabhata mentioned. In the medieval ages, in the 17th century, Galileo started doing experiments by rolling things on an inclined plane like this. And he tried this with various experiments with various kinds of devices. So he had two cylinders of different mass, two cylinders of different size, hollow cylinders of different size. Everything he measured on a similar slope, and he observed certain things. Generally, he observed that a cube, if a frictionless cube or a cylinder or a sphere, if you drop them, they all fall at different rates. This is what Galileo observed initially, and this is what we thought it should happen. But in an ideal case, when he did this experiment perfectly, he realized that things that fall down towards the earth, maybe a heavier cylinder or a heavier ball. Many of us are familiar with this idea that Galileo went to the Leaning Tower of Pisa and went to the top and then dropped objects. So he believed that a heavier object would fall down, just like Aristotle mentioned. But then uh, what he observed was that when he dropped two objects from the Leaning Tower of Pisa, both fell with the same speed, both fell down together at the same time. So this is something completely different than what Aristotle has mentioned. This is completely different than the ancient philosophy that we had regarding things falling down. We thought bigger objects, heavier objects fall down faster. But Galileo observed that things fall down together. Even though if one is heavy and one is light, they would fall down together. They did this experiment in space as well, and they found the same result. Things fall down together. So this is one of the NASA astronauts when they went to space. They took a hammer. I'm not sure if it's very clear in the image here. He's dropping one hammer and one feather-like thing in space, and then it falls down together at the same velocity. So this is something they observed in space through NASA. So when we talk about gravity, we will come across certain ideas like the Kepler's law. Kepler's law is something that tells us what governs the universe, what how orbits move. So we need to study that also when we understand gravity. Kepler's law says that objects move around other objects in elliptical path. So ellipse is basically a circle that is stretched. So if we have planet like the Earth, then the sun is at the one point around which the Earth moves. And Kepler said that this orbit is not a circle, it is an ellipse, such that sun is at one of the foci, which means for an ellipse, there are two focus points. I hope all of you know what an ellipse means. Ellipse is something, it is like a figure that is drawn such that every single point, I can switch to laser pointer, I think, just a second. Yeah. So each one of these points on this line, let's say some point here, this point, if you take this point, then distance between the sun and this point and distance between this point and this focus, that too, if you add up, then it will be equal to the same calculation if you do it here. It will be the same calculation if you do it here. It will be the same calculation if you do it here. So we call an ellipse as a locus of all the points such that the sum of its distance, sum of their distance from the two foci are equal, are the same. So if you take the sun from here to here, here to here, it's the same distance as here to here, here to here. So this is how an elliptical path is. And Kepler said that sun or whatever is the parent object should be at the one of the focal points. And the object orbiting is usually in an elliptical path. Then came the idea of an apple falling down on the famous scientists' heads. We realized that when an apple fell down, Newton realized all this was what led to the theory of gravity. When an apple fell down on Newton's head, Newton realized, why did the apple fall down? There must be something pulling it down. If an apple comes down, then it should also go up. Why does it not? So there should be something that is pulling the apple down towards the earth. And then he slowly figured out that this is what is causing the earth to rotate around the sun as well. So Kepler said the earth is going around the sun. Okay, it was Copernicus who gave the original theory, but Kepler who said it's in an elliptical path. And then Newton said this is because of gravitational force. And then he said that he gave a law, which we all know as every particle attracts every other particle in this universe with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Now, to put it in simple terms, what it means is if you have two objects, let's say one big object of mass capital M and one big object, small object of mass small letter m. And these objects M1, M and capital M and small m are separated by a distance r. then Newton says that the force acting between capital M and small m masses is directly proportional to capital M, directly proportional to small m, and inversely proportional to the square of radius or the distance between. Which means if you double capital M, force will double. If you double small letter m, the force will double. If you double small letter r over here, then F will fall down. It will be 1 by r square. So if you make r is 2r, then it will fall by 1/4, and force will also fall by 1/4. So we combined all these proportionalities, and then we got the Newton's equation, that is F is directly proportional to mm by r square. And of course, I don't want a proportionality, I want an equality. So I add a proportionality constant. Newton calculated this G and found out that G, which we call the gravitational constant, is equal to 6.674 into 10 power minus 11. Now, what is the unit of this G? I will leave it to you students. Okay, you can maybe send the answers to the organizers. What is the unit of this G here? You should be able to calculate this by cross multiplying this whole equation here, putting all the terms on with the F and keep G as it is. So the unit of G would be something that is up for the students to identify. The value of G is 6.67 into 10 power minus 11, which means if I have an object of mass 1 kg and another object of mass 1 kg, when you multiply that, let's say they are separated by 1 meter, then force should be 1 multiplied by G, which is 6.6 into 10 power minus 11, which is very, 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 very small number. So the force also would be very small. Newton also mentioned about another law. This was before the gravitational law actually. He mentioned that the rate of change of momentum is directly proportional to force acting on it and takes place in the same direction as the force. So if an object is moving forward, it has something known as momentum, right? Mass into velocity for that object is momentum. So Newton said that the rate with which this momentum changes, this rate is directly proportional to force acting on the object. So if a force is acting on an object, its momentum will change, and that rate of change is directly proportional to the force. And also it takes place in the same direction as the acting force. So if I push it from top right to left, the object will move, the rate of change will occur from right to left. So this is the equation he gave you. We know P is equal to mv. So dp by dt is directly proportional to force. Okay, this is Newton's law, and you just substitute for P. Uh, at this point, you should understand that P is equal to mv, and because m is a constant and it's not a vector, I can take it out of the d by dt. Okay, from the differential. So I have m into dv by dt is directly proportional to f. So if you're studying gravitation or if you're learning this for the first time in your PU, then by now you know that dv by dt is something. dv by dt is acceleration. So I can write m into dv by dt as m into a, which is equal to f. In reality, there's a k over here. There's a proportional sign over here. So there should be a k over here. But I can define f such that that k is equal to 1. So ma is equal to f, right? So any object, if it is having a mass m and it is stationary, it is standing somewhere, and I apply a force on it, then that force will lead me to an acceleration a in the same direction as the force. That is very important. Now, you have two objects. Gravity means something is falling down towards the earth, which means it is attracting the object. Earth is attracting the object. If I take an object like this and I drop it down, then it falls down because earth is pulling it down, right? So gravity is causing things to fall down. At the same time, if there is a gravitational force, then there has to be an acceleration downwards. The moment I leave this object, then it will come down with an acceleration. Let's call this acceleration as g for now, because it's an acceleration that comes because gravity is pulling down. I will call it acceleration due to gravity. Now this acceleration is g, and it depends upon with what force the earth is pulling it down. Okay, so I have two equations for force. Okay, gmm by r square and mg. And if the force is gravitational, which means gravitational force by the earth on this object is what is causing this force as well as this force, then I can equate the two. And now you realize that there is a small m in left hand side, there's a small m in the right hand side. I can cancel them out, and I'll get G is equal to GMM by R square. Okay. Now here G is called the acceleration due to gravity. I can calculate this for you. You put G value, which I showed you a while ago, 6.6 into 10 power minus 11. And for M mass, you put 5.97 into 10 power 24, which is the mass of the Earth. 5.9 into 10 power 24 kgs. Okay. Now, what is R? R is, let's say, the radius of the Earth. I want to measure G at the surface of the Earth. So at a distance of R, uh, let me put this R as 6371 into 10 power 3 because it's kilometers. 6371 10 power 3 meters. Okay, because it's R square, I'll square the number. So when you do this calculation, you will get 9.81 meter per second square. Now, just take 30 seconds and identify the unit there. How does G get meter per second square? That is something you need to understand. Okay, how does G get meter per second square? So if you observe, I told you G is acceleration. Acceleration is rate of change of velocity. So rate of change of velocity means velocity per unit time or velocity by second. Velocity unit is meter per second. So meter per second is meter per second square. Okay. So here we have G is equal to 9.8. Now this I got by substituting mass of the Earth and the radius of the Earth. So can you substitute the mass of Mars with the radius of Mars and get G? Let's find out. So before I proceed further, you need to understand what do you mean by mass and weight. Okay. On Earth, it is very confusing because all of us, when we go and measure something, we are basically measuring our weight, but the computer or the device tells you your mass. We say my weight is 65 kg, but it's not really the case. An object falling towards the Earth falls with an acceleration of 9.81 meter per second squared, and the gravitational force acting on this object is weight. Okay, it's the gravitational force on the object is weight. The unit of weight should be the unit of force, not unit of mass. So when I say weight is 60 kg, it is wrong. Okay, the device is calculating that your force is this much and telling you your weight. So an object weighing 40 kilos, okay, on Earth, you need to calculate this by 40 into 9.8 meter per second square. 940 into 9.81, and you would get 392.4 Newton. You see, when I say 40 kgs, it is not the weighing. It's not the weight, it's actually the mass. Okay, this is the mass. And the weight of an object is usually given in newtons. So when you measure your weight and you observe something, you are basically measuring it in newtons. But the device that you use to measure usually has an inbuilt calibration to tell you that if the force observed is 392.4 Newton, then show the number 40 on the screen. And that's how you say your weight is 40 kgs. It's a wrong notion. Mass is 40 kgs. For 40 kilos mass, the weight on Earth is 392.4. Why? Because here uh, weight is mg and g depends upon the planet's mass and radius. So here, if I substitute for, let's say, mass, g of mass, then I should get, if I substitute g of mass with 40 kgs, I should get weight as 142.10 Newton. So with this, you can say both the masses were 40 kgs. Here G was 9.8, you got 392. So here G of mass is more or less than the Earth is something you should be able to identify because you are getting a lesser number, 142.1. Okay. So an object of 40 kgs will remain 40 kgs everywhere, but its weight will change from planet to planet. This is something very important. Okay. Fine. Yeah. So you can get this number by multiplying Mars's acceleration due to gravity, which is 3.72, which is obviously lesser than Earth. So these are the various masses and radius for various planets. You can take a screenshot probably and calculate G for these planets yourself. Now let's use some numbering things, and these are very important for competitive exams. 1 kg stone on Earth will weigh 9.8 Newton. Okay. So on Mars, what will it weigh? 1 kg, so m is 1, right? 1 kg, m is 1. So F is equal to mg. 1 kg into 9.8, I'll get 9.8 Newton. Okay. But for mass, I have G by R square, which gives me 6.674 into 10 power minus 11, which is your G, capital G. And then for mass, the mass is 0.107 with respect to Earth. It's not an absolute mass, it's with respect to Earth. So if Earth's mass is 1, Mars's mass is 0.107. So you can have 0.107 uh, related to Earth's mass. So I substitute 0.107 into Earth's mass. Similarly, related radius is 0.533. So 0.533 into Earth's radius whole square. So this is what I calculate, and I should get mass as 3.78 meter per second square. This is the calculation of it. Okay, 3.78 into 10 power, into 0.78 meter per second square. So 1 kg of rock on Mars will weigh 1 kg because its mass is 1 kg, but its weight will be 3.78 Newton. On Earth, it's 9.8. On Mars, it is 3.7. So weight of an object changes from planet to planet, but its mass 1 kg will remain the same. For Jupiter, you can do the same calculation. You'll get G as 24.84. So naturally, a 1 kg stone on Jupiter will weigh 24 kg on, 1 kg weight on Earth will weigh 24.8 kgs on Jupiter. Okay. Its mass will not change. It is just how you measure the weight will change. Now coming to free fall. Free fall is something when you fall without the influence, under the influence of gravity without being constrained. So an object in free fall is falling down without being held up by anything. It is simply falling under the influence of gravity. So these are the skydivers that we usually see that are under free fall. Okay. So when you do free fall, you are basically falling down, right? I'm not sure if it's visible here. Yeah. You're falling down. The plane is not going up. You are falling down. You're falling towards the earth, and your acceleration is usually 9.8 meter per second square. Okay. So when you're in free fall, you will fall with 9.8 meter per second square acceleration. That is the rule for everyone. So when you talk about an object falling down, it will fall with an acceleration of g, which I said is 9.8 on earth. So from Newton's equation, I can write v square minus u square is equal to 2as. V square minus u square is equal to 2as. This is Newton's laws of motion, equations of motion, the third equation. So if I take this equation, initial velocity, whenever something is falling, okay, whenever something is starting to fall, its velocity starts from 0. So u is 0. V square minus 0 is equal to 2gs. Because it's falling under gravity, I put g. There's no other acceleration. And if I substitute, I'll get v is equal to root of 2gs because there's a 0 here. And I'll simply take the value of g I know, which is the formula g n by r square. And I'll combine this. Okay. Now velocity is distance by time. So I'll put s by t. And this root of 2gs, I'll write it as this. Okay. This is supposed to be s square over here. So let me just change it for you. Okay, so it's supposed to be x square because you see I have removed the square root. This is square root here. Here there's no square root. Okay, and there's an s over here. There's an s over here. I just skip a step so I'm making it full. So you see I've removed the square root. It's 2gs, 2gs. S by t becomes s square by t square. Now what happens? Because there's an s over here, there's an s over here, I can cancel this s with this power. So power 2 becomes power 1. S power 1 by t square is equal to 2g. Okay, I hope you're able to follow this. So I'll write s divided by t square is equal to 2g. Or I'll just cross multiply and write t square is equal to 2 s by 2g, or t is equal to root of s by 2g. Okay, what does this tell you? It talks about the time taken by an object to fall down. Time taken by an object to fall down for a distance s. If an object is falling down from a distance s, let's say 1 meter, then the time taken for that object to fall down is root of 2g. Look at the beauty of this equation once. This equation tells you that the time depends on s, which is the distance with which you raise it, and g. G depends upon the distance of the object and the earth and the mass of the earth. Where is the mass of the object? It's not there in the formula. So in the time taken by the object to come to earth, there is no uh, there's no term that says the mass of object. Simply, object mass does not matter at all. Okay. So two objects falling from the same height, if S is same, then G is same for everyone on Earth. So if S is same, T is also the same, which means two objects falling from same height fall together. And this was done on Earth. On Earth, we took a chamber and we evacuated the chamber, which means we removed all the air from the chamber. And then we dropped two objects. You can see in this video, this was done by BBC. In this video, we have a bowling ball, which is easily 7-8 kilos. And then we have thread. We have a feather. So when a feather falls, usually if there is air in the room, the air keeps the feather flying and the feather will never fall down. But here you can clearly see both of them drop together. The feather and the bowling ball come down together at the same time. So in space also, under gravity, there is no air. On many planets, there is no air. So there you can go and do this experiment, you'll find the same result. That irrespective of the mass of the object falling, the time taken for two objects of different masses will be the same, because it only depends upon the radius of the Earth as well as the mass of the parent planet. Now let's talk about a simple pendulum. Simple pendulum, all of us have experienced it, I think. It's basically a thread connected with a bob at the end. This bob has mass m. So whenever I'm lifting the pendulum, I'm kind of giving it a swing. I pull it on one side, then that these are the forces on the pendulum. There's mg acting downwards, mg cos theta acting along the string, and mg sin theta acting perpendicular. Okay. Now here the time period of the pendulum depends on g. This is something we learn. You have studied this formula. The time period of a simple pendulum depends upon 2 pi and root of Lg, L by g. 2 pi is a constant, I think all of you know this. L is the length of the string. So if I change the length of the string, the time period will change. And also the small g, it depends upon g, which is a constant for the Earth. Which means on Earth, if I take a simple pendulum made out of a bob, the time period for that pendulum is 2 pi root of L by g. And if I remove the bob and connect a big, high weight object, let's say 10 kg stone, you'll realize that 10 kg stone's mass is not in this formula. Therefore, it doesn't really matter. This pendulum will swing at the same rate as it does for a bob. Okay. So now if you throw objects on Earth, the farther you throw, faster you throw, the farther the object will be. If I throw an object, it will fall like this. If I throw an object faster, it will fall like this. If I throw an object faster, it will fall like this. Now let's say if I throw much more farther, it should go around and fall and land somewhere here, like it's shown in this image over here. It's falling in this part, right? Now what if you can shoot it with some velocity such that for one velocity, we saw that it falls here. For second velocity, we see that it falls farther. But let's say you throw it with such a velocity that it will try to fall down, it will try to fall down, try to fall down, try to fall down. But when it falls down, there's no earth over here. So it'll go around search of earth, come down, I want to hit you, I want to hit you, it'll come down, and finally hit the back of the camera. So there is a very high speed velocity that you can actually think of, such that if you fire something at this velocity, it will simply go around and come from the back. Okay. This is something very beautiful about gravity. Okay. So if you throw harder, it will not find land to land on. So it will go around the Earth. And by this, I get the orbital velocity. Whenever an object is going in a circle like this, it has a centrifugal force. And this centrifugal force is outwards. Okay. It's always outwards. So it's always from this to here, this to here, this to here, this to here. And that is not going so, because object is not going away from the Earth, it is falling towards the Earth, it is attracted by gravity. But gravity is not also too much, because if gravity was more, then it would have fallen to the Earth. It's not falling to the earth. So gravity is making it go around, but it's not falling to the earth because gravity is balanced by the centrifugal force. So if I equate the two equations for centrifugal force, I can always write the force as mv square over r. And I know from Newton's laws, F is equal to gmm by r square. So if I equate this two, let me take r as the radius of the earth. Okay. Uh, the capital R is the radius of the earth. H is the height at which the object is located, or the satellite or whatever is located. And small r is the distance of the object from the center of the earth, shown here. And let's say v is the velocity. So if that happens, then I can write F is equal to mv square. Okay. I have simply put the orbital velocity here. So I've got mv square from here, this equation. But instead of this r, this distance, you see that this is nothing but radius of the earth plus height. So r plus h. So mv square over r, I can write it as mv naught square over r plus h. Okay. And I can write the Newton's equation as F is equal to gmm by r. R here is again r plus h. So gmm by r plus h whole square. I will equate the two equations here. You see that there's a common m here and m here. And there's an r plus h here and there's an r plus h whole square here. So I can cancel the m and m here. And if I cancel this r plus h, I will have to remove this 2 and make it 1. So in the end, I'll cancel the terms and I have v naught square is equal to gm by r plus h. V naught square is equal to gm by r plus h. It's not really v naught, it is vo because it's the orbital velocity, the velocity at which the object is orbiting. So the orbital velocity is equal to gm by r plus h. This is something new. So I don't like square roots. I don't like squares. So if I want to find the exact value, I'll take v naught is equal to orbital velocity is equal to root of gm by r plus h. This is the orbital velocity. And now you know that gm by r squared is nothing but small g. So I already have gm here. Okay. So I'll take this r squared here and cross multiply it with g. So gm this here becomes equal to gr squared, which is what I've done before. Okay. Now again, orbital velocity does not depend upon mass anywhere. It only depends upon the orbital height r, which is again the product of r plus h. Okay. And you can write this as r plus h is equal to r, right? R plus h is nothing but r. So gr square by r, which is root of gr. Okay. For small heights, it's the same capital R. Otherwise, you can write it as small r. V naught is equal to root of gr. For Earth, I can calculate this. G is 9.8, R is 6,400 kilometers. So 6,400 into 1,000 meters. And if I calculate that, I'll get the orbital velocity is 7.92 kilometer per second. Which means if I want to put something in orbit around the Earth, I need to throw it with a velocity of 7.92 kilometers per second. This is when R is very close to H. Okay. Let's say the radius of the Earth is 6,400 and 6,400 kilometers, and the orbital height is 1 kilometer. So compared to 6,400, 1 kilometer is nothing. So at 1 kilometer orbit, you'll get somewhat similar orbital velocity. You see from this equation that the orbital velocity will reduce as you increase the height, because h is in the denominator here, r is also there. So when you raise h by a large amount, this will raise, these two will raise, but this is square root. So you need to go faster. Now, how do I measure orbital period? What is the time taken to complete one full orbit? The time taken to complete one full orbit is given by the simplest formula. Velocity is equal to distance by time. So you have velocity, which is the orbital velocity, and the orbital distance, which is basically the circumference of the orbit. So the orbital distance divided by time. Orbital time is the time taken to complete one full circle around the Earth. So orbital velocity is equal to orbital distance by orbital time. So you have root of gm by r plus h is equal to 2 pi r plus h by t. Okay. So this is your velocity equation. This is the radius. This is the radius of orbit r plus h. 2 pi r is the circumference. So circumference, which is a circular orbit, divided by time period, which is t, time taken to complete orbit. So you cross multiply a little here and there, and you'll get this same equation in the other form. And here I can simplify it like this. I will take the square root by squaring it on the left hand side. I get t square divided by 4 pi square into r plus h whole square is equal to r plus h divided by gm. Or the orbital period time t square is equal to 4 pi square r plus h whole cube gm. Okay, I'll substitute the height, the radius of the earth and the mass of the earth. So I'll get t square is equal to 4 pi square 6.4 10 power 6 plus h. I don't know what the height is. Divided by mass of the earth 6.674 into 10 power minus 11. And we have, sorry. Mass of the earth, which is 5.97 into 10 power 24. And the capital G, which is gravitational constant, which is 6.674 into 10 power minus 11. So when you do this calculation, okay, I will cross multiply here. Okay, I'll take the denominator and multiply it with t. I'll put the 4 pi square in the numerator and cross multiply it to the denominator. And all I've left is this. Or let me simplify it further. Okay, I'll take a cube root of this. I will take a cube root to remove this. So this whole thing becomes cube root, which is power 1 by 3. I hope all of you know this. Something squared is power 1 by 2. Something cubed is power 1 by 3. So I have uh, this whole term. Which one was it? This whole term, the third cube. Okay, the third cube of this whole term minus this term, because these two are plus only. I have multiplied everything with square root of 3. So this bracket will go, this 3 will go, and this equation will be power 1 by 3. This equation power 1 by 3 is written over here. And here, because there's no 3, there's no point in putting brackets. So I have the same number. But 6.4 into 10 power 6, I have taken it on the other side. So you can see it is minus 6.4 into 10 power 6. Okay. A little bit tedious calculation, but if you take a screenshot and work it out, it's very easy. We just need to know the value of mass of the earth and the radius of it. So, is the time period same as the Earth's rotation period? Then what will happen? For an object, the time period is the same as the Earth's rotational period. So, as the Earth rotates on its own axis, we see stars go around in once in 24 hours, 23 hours, 59 minutes. The sun and the moon, they'll also go around in a circle, rotating around the Earth. Okay. But the speeds are different. So, let's assume something is going around the Earth with the same speed as the Earth's rotational period. Then what will happen? So yeah, the rotational period is 23 hours 46 minutes 34 seconds. I'll plug in that number, which becomes 86,164 seconds. And when I plug in that number for t over here, I will get h in the following manner. I'll get h as 3.57 into 10 power 7 meters. Which means if I put something at 3.58 into 10 power, let's say there's 2 decimal places here. So 10 power 5, remove 3 decimal places, it becomes 35,800 kilometers. Which means if you put a satellite in an orbit at a height of 35,800 kilometers, its orbital velocity will be the same as the time period on Earth, which means the satellite appears to be stationary in the sky. Therefore, we call it a geostationary altitude. Okay, a geostationary altitude. Right? For the real value that we have found today is 35786 kilometers. Okay, so such satellites that orbit around the Earth with the same speed as the Earth's rotation, when you look at it from Earth, appears to be stationary. It does not move. So such satellites will be difficult to identify because they don't move in the sky. Right? So this is called a geostationary orbit. You see here, they say that they shown that the satellite is above Brazil, and as Earth rotates, the satellite is always above Brazil because you see the Earth and the satellite orbit or rotate at the same speed or same time period. Gravitational potential, this becomes a little tedious, so let me go a little quickly. The work done bringing an object from infinity to some distance r is called as gravitational potential. So dw is f dx, which is all of you know, work done is force into displacement. So f is force, dx is displacement. Okay, so dw is equal to f, which is gmm by x square into dx. Now here is where it gets interesting. Because I want to find the work done, I need to integrate this so that this becomes W, not dw, it becomes w. Okay, so to make it w like this, I have put a integration. I've integrated from infinity to r. I've integrated from infinity to r because I'm bringing an object from infinity to that distance, and I'm taking the integration of this dw, which is gmm by x squared. Okay, so I can do this calculation. G, capital M and small m are all constant. They don't need to be in the integer symbol. So I put it out and I write gmm into integration infinity to r 1 by x squared dx. I can simply simplify. 1 by x square is nothing but integration becomes 1 by x. Apply the limits r and infinity. Okay, it's supposed to be minus 1 by x, and that's why this minus is written outside over here. So I'll apply the limits. 1 by x becomes 1 by r minus 1 by infinity. 1 by infinity is 0. Therefore, w is equal to minus gmm by 1 by r, or minus gmm by r. Okay. Work done is minus gmm divided by r. Now, the gravitational potential. This is defined by the work. Okay. The gravitational potential that is defined by the work done is therefore written as minus gmm by r, which is coming from this formula here. Minus gmm by r. How an object will escape its gravity? How an object will escape its parent object's gravity? If I am on Earth, I want to jump up such that gravity does not pull me back. Then I have to move in a way from Earth with the kinetic energy opposing the gravitational pullback. Which means when I'm in a rocket, I'm going from a height. Okay. When I'm on a rocket, uh, yeah. So I'm on a rocket and I have to escape the gravitational potential. So just okay. Yeah. So to escape this, what happens is I need to escape the gravity and I need to have that much potential energy. Okay, kinetic energy must be there to overcome the potential. And therefore, I write U is equal to minus gmm by r, which is the potential. And I equate that to the kinetic energy, half mv squared. So when I equate these two, I will get gmm by r is equal to minus half mv squared. Now I am trying to escape the Earth's gravity. So I will call this velocity as escape velocity. Okay, so I'll equate this equation. I have two m, one m here and one m here on the equation symbol. Both sides I have m. I can cancel them. So when I cancel them, I have 1 by 2 ve square is equal to gm by r, or I'll cross multiply this 2 and I'll get ve square is equal to 2 gm by r, or simply v is equal to square root of gm by r. Okay, now this is the velocity I need to escape Earth's gravity. And again, this formula depends upon g, which is the constant, m, which is the mass of the Earth, and r, which is the height from which it is launched. It does not depend upon the mass of the object. Okay, it does not depend upon the mass of the object. Fine. So this is the formula for escape velocity. So escape Earth gravity, let's substitute the values of G, M, and R. G is 6.6 into 10 power minus 11. M is 5.972 into 10 power 24. And R is 6371 into 10 power 3. You multiply G, M, and 2 over here. And then you divide it by R and take the square root. You will get 11.6 kilometers per second, or 11,600 meters per second. Right? 11.6 into 10 power 3 meters per second. Similarly, for Mars, if I have to do, I have to substitute Mars's mass and radius. So what I do is I take the relative mass of Mars, which is 0.107 times Earth's mass. 0.107 times Earth's mass. Similarly, 0.533 times Earth's radius. 0.533 times Earth's radius. I've taken the relative mass and radius, and I've substituted it here in formula, and I find that to escape Mars's velocity, you just need 5020 meters per second, or 5.020 kilometers per second. So it's easier to escape Mars's gravity. For Moon, again, I've made a mistake here. This is not Mars, this is Moon. For Moon, We substitute the mass of the moon, which is known to us, 0.735 into 10 power 24, and the radius of the moon is 6 times smaller than the Earth, so 1740 into 10 power 3. When I substitute the values and calculate, I should get the escape velocity of moon is 2.38 meters per second. So you need very small velocity to escape moon's gravitational field, but you need very high velocity like 11.6 meters per second to escape Earth's gravitational field. Okay, so these are the values that I mentioned earlier. So here is a table that lists out all the gravitational acceleration as well as escape velocity for various planets. For Earth, I told you it's 9.8 meters per second square, and the velocity is 11,200 or 11.2 meters per second to escape the Earth's gravitational field. On Mercury, g is very small, so the velocity required is also very small. On Jupiter, g is very large, so this is 9.8, it becomes 24.8. It's a very large number, so therefore the velocity will also increase to 60,000. Okay, 60,000. Similarly, Saturn and Uranus, velocities and g is given here. Okay, so now if you want to escape the gravity of something else, okay, let's say the sun. If you want to escape the gravity of the sun, then you need to substitute m and r from the sun. And when you do that, mass of the sun is 1.98 into 10 power 30, and radius of the sun is 696,340 into 10 power 3 meters. When you substitute this, you will uh, basically get the value as 615000. That is 615,000 meters per second, or 615 kilometers per second. So the escape velocity of the sun is very, very, very high. But what if? What if this velocity was close to the speed of light, or was equal to the speed of light? You know the speed of light is 3 into 10 power 8. Okay, you know the velocity of light is 3 into 10 power 8 meters per second. So you put, instead of v, you put c. Okay, you put, instead of v, you put c, and then you get c square is equal to 2gm by r, or r is equal to this some radius, or this is the distance. So radius is equal to 2gm by c square. Now here c is a constant, g is a constant. So what does r come from? It comes from m only. If m is changed, r will change. And this r is called the Schwarzschild radius for that particular mass m. So let's understand this better. Schwarzschild radius is that radius such that it forms a kind of a planet where the escape velocity is speed of light. And if the escape velocity is the speed of light, nothing can escape. Even light cannot escape. So if light cannot escape, nothing comes from that object. No light will come from that object. Therefore, it should appear as a dark object. And that is what we call it as black hole. Okay. Where for certain mass of the black hole, RS is the Schwarzschild radius. Now coming to center of gravity, we have whenever an object has distributed mass, somewhat irregular or kind of a different shape, it has two objects called the center of gravity and center of mass under a uniform gravitational field. If the gravitational field is not uniform, like if you are closer to the sun than the earth, or if you're closer to the earth than the moon, then center of mass and center of gravity may vary for that object, whichever you measure. Similarly, for a same object uh, kept in different orientation. So if you have a disk that's kept in such a way that it rolls, then its center of gravity here is in the center and it's pointing downwards. For an object that you put down on the floor, the center of mass is the same, but it's distributed in a different way now. And for a kind of a what do you call it? A hollow disk. Even though there is no mass at the center here, everything is at the edges. This is as good as the center of mass over here, as if all the mass is fixed over here. When we talk about gravity, everything is being pulled down by gravity, but anything can be balanced until and unless the center of gravity is between the balancing point of the object. For example, for humans, we have two legs. If your center of gravity is between your legs, then you can balance. If your center of gravity is almost up to the edge, such that it's on the leg, then also you can balance. But if a center of gravity goes beyond the two balancing points or three or four balancing points, then it is unstable. It's going to fall. That is the importance of center of gravity. The same thing with yoga. When you do yoga, you basically maintain the center of gravity such that no matter what pose you do, if the center of gravity is between the two, what do you say, points where you're standing on the ground, then you'll be able to stand properly. There's no problem there. Okay. Now, understanding something about the lift. If you're if you observe that when you get into a lift and the lift starts, when the lift starts, we kind of feel heavy if the lift is going up, or a lift is going down, we feel lighter. So in such a case, we can calculate it by equating your gravitational force mg with that of the acceleration or the force caused by the acceleration of the lift. In such a case, for a person in a lift where the lift is stationary, a is 0, so there is no difference felt. You see, your weight is the same. You apply it in this equation here. Acceleration of the lift is 0, so the weight is not felt. It's a very important formula for competitive exams. They can simply give you, if you have two lifts, then one lift is moving faster, twice as fast as the other lift. Then on which of the lifts you'll feel more weight, right? Or more lighter when you go up. That things you need to understand. Okay, those are very important questions. If the lift is going down, then it is coming down with an acceleration of g. Okay. Oh, sorry. If the lift is going up, if the lift is going up, we take g as positive. So if the lift is going up, the acceleration of the lift is equal to g. So you're feeling twice as heavy, and therefore you feel very heavy in your legs. If the elevator is going down, then we put the acceleration of the lift as minus g, such that a and the acceleration which is minus g will cancel out the g from the natural gravitation of the earth. Therefore, you will not feel any weight. We call this weightlessness. Okay. So for first case, acceleration is 0, we get w is equal to mg, which is normal. For the second case, we add a is equal to g, so mg plus ma, which is 2mg, right? G is equal to a, you put a is equal to g here, you get 2mg, you feel twice as heavy. And in the third case, you put a is equal to minus g, and you will get 0. So your weight will be 0. Your mass is still the same, your weight is 0. So what causes gravity? Newton tried to explain to us gravity is a consequence of nothing. He simply said gravity is a phenomenon. He said the gravity is there everywhere in the universe. It prevails across all objects with some mass, and everything will be attracted because of gravity. But it was Albert Einstein in 1905 who told us that if you are in a lift and you're freely falling, like I told you here, if you're in a lift and you're freely falling, if the lift is cut off, then there is no weight felt, as if there is no gravity. You will float inside. So Einstein said that gravitational field is equivalent to an accelerating field, which means you're accelerating downwards, right? You're accelerating downwards in a lift and with the same g, right? With the same acceleration as g, so you do not feel any weight. And that is what Einstein said. They are equal. Acceleration and gravitation are equal. This is called the principle of equivalence. If you're on Earth, if you drop a ball, it's going to fall down. If you're in a rocket and if the rocket accelerates up, then the ball is going to fall down as if there's a gravitational field inside the rocket. This is called the principle of equivalence. And this is the equation given by Einstein. For PU level, this is very, very difficult. Even for degree BSc level, it's very, very difficult. But this is the actual equation which even Newton did not tell us is what governs the gravitational force. So Einstein said, because of that equation, space-time is bent around object, and like a rubber sheet, you drop a marble inside, it's going to go roll, 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 and fall towards the object. So everything falls down because of the bending of space-time. And in the future, if you continue the study of gravity, you can think about or you can pursue your research or your studies in fields like gravitational wave. In India, we have the LIGO coming up, LIGO, where gravitational waves will be studied through experimentation. So that is the future for all of you. Here, reference book I used. You can use these books to understand gravity better. Resnick and Halliday has beautiful equations. Concepts of physics also are the same things that I've covered. to understand relativity better or gravity better, which I have explained in the last two slides, you can use this book by Einstein. Okay. And this is my email ID. If you have any questions, you can ask me on my email ID directly also. So with that, I've completed this session on gravity. But gravity is a very important topic because competitive exams, they can ask you very simple questions. For example, like I mentioned, you're in a lift. You have two lifts, A and B. One lift is moving up with some acceleration, A. The second lift is moving up with an acceleration of half of the first lift, 0.5 A. Then in which lift you will feel lighter, or in which lift you will feel heavier, by how much? Or if you have an object that is like, let's say you have a planet which is 5 times the size of 5 times the radius of Earth and twice as massive, 2 times the mass, then what is its escape velocity, or what is its orbital velocity, or what is its orbital period? So these are all small problems that you can find out in competitive exams, which can fetch you easy marks, provided you know these formulas very easily. So with that, I would like to end this session. If there's any questions, I would like to address them, please.
ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ ನೋಡಿದ್ರೆ ಸರ್, ಅದು ಯಾರೋ ಒಬ್ರು ಮಂಜುನಾಥ್ ಅಂತ G is nm square per kg square ಅಂತ ಕಳಿಸಿದ್ದಾರೆ.
ನೋಡ್ತಾ ಇದ್ದೀನಿ. Yeah. Unit of G is nm square by kg square. Good. That's what we are looking for, because force is Newton. Mass into mass becomes m square. Sorry, kg square, and r is meter square. When you cross multiplying, it becomes f into r square divided by m square, which is equal to G, and the unit is G is equal to nm square by kg square. Very good, Manjunath. The answer is right.
One more question from Pooja Jewur. kg m cube second square.
Yes. That needs to be correct. I mean, maybe there's a small correction error. You can just verify it. Okay. If you have any questions, you can ask. You can post it in the chat
ಸ್ಟೂಡೆಂಟ್ಸ್
box.
ಏನಾದರೂ ಕ್ವಶನ್ಸ್ ಇದ್ರೆ, ಈ ಇವತ್ತಿನ ಟಾಪಿಕ್ ಮೇಲೆ ಏನಾದರೂ ನಿಮಗೆ ಡೌಟ್ಸ್ ಇದ್ರೆ, ನಮ್ಮ ಅತುಲ್ ಭಟ್ ಸರ್ ನೇರವಾಗಿದ್ದಾರೆ. ಸೊ 1 to 1 ಕೇಳಿ ಆ ಡೌಟ್ ನ ಕ್ಲಿಯರ್ ಮಾಡ್ಕೊಳ್ಳಿ. ಸೊ ಫರ್ದರ್ ಕ್ವಶನ್ಸ್ ಏನಾದ್ರು ಕಳಿಸಿದ್ರೆ ಸರ್, ನಾನು ಐ ಸೆಂಡ್ ಥ್ರೂ ಮೇಲ್ ಸರ್.
Okay, sure, sure.
So anyway, thank you, sir.
Thank you, sir.
Today is the very informative talk on gravitation. ಬಗ್ಗೆ ಬಾರಿ ಸರಳವಾಗಿ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ತಿಳಿಸ್ಕೊಟ್ಟಿದ್ದೀರಾ. ಸೊ on behalf of KSJ and myself, thank you, sir. Thank you very much.
Thank you.
And I also thanks to our KSJ CEO, sir, Dr. Ramesh sir, and Director J.P. Basharaj sir, and also I thankful to all the attendees. ಸೊ ವಿದ್ಯಾರ್ಥಿಗಳೇ, ನಾಳಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಚಂದ್ರಶೇಖರ್ ಶೆಟ್ಟಿ ಸರ್ ಅವರು ಸೆಮಿ ಕಂಡಕ್ಟರ್ಸ್ ಮೇಲೆ ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದು, ಎಂದಿನಂತೆ ತಾವು ಹೆಚ್ಚಿನ ಸಂಖ್ಯೆಯಲ್ಲಿ ಹಾಜರಾಗಿ ಆ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವನ್ನು ಕೇಳಬೇಕು ಅಂತ ಹೇಳಿ ನಮ್ಮ ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ಮತ್ತೊಮ್ಮೆ ತಿಳಿಸುತ್ತಿದ್ದೇವೆ. ಸೊ anyway, once again I thank you, sir.
Thank you, sir. Thank you so much.
Okay.